Okay, so we were talking about these systems, fixed points and stability. Do you remember? So basically, uh, we show fixed points by the filled circles, stable ones with a filled circle, unstable ones with open circles, and in general, a picture like this is called phase portrait. Okay. Okay, let's move on. Now, uh, we also talked about this in the break, but let's read it from the book. Fixed points dominate the dynamics of first order systems, this n equals 1 systems. In all our examples so far, all trajectories either approach the fixed point or diverge to plus or minus infinity. In fact, those are the only things that can happen for a vector field on the real line. Okay? Those are the only things that can happen. Again, do you see the connection with Poincaré's way of thinking? Like, do you remember the question of whether the planets would fly away or not? So you can see that here we connect qualitative effects. Looking at it geometrically, pictorially, we are actually connecting dynamical systems with topology, right? Basically, what can happen on a line? You can either go to a point or go to infinity. Of course, given that you have to act according to this function that crosses the line. So let's give some examples. Like if you have something like this, if fx is always positive, it means that you will always go to plus infinity, right? If it's something like this, you will always go to minus infinity, right? And if it goes like this, which point is the stable fixed point? This one, right? Because over here you go to the right, over here you go to the left. And this one is an unstable fixed point. What about a system like this? Do we have a fixed point? Yes, we do. Is it stable? No, it isn't. It's unstable. If you start here, you go to minus infinity. Start here, you go to plus infinity. Very easy, right? So now let's look at an example, a real life example, RC circuit. Do you remember, uh, if you were not really fond of physics, you had to actually memorize the solution of these equations, right? Basically, you can write down Kirchhoff rule for this system and you will get something like this. Do I need to derive this equation? No, right? But let's now that we are armed with this geometric way of thinking, let's look at this system. What do we have? We have Q dot equals to V0 over R minus Q over RC. Do you see it? Just trust me that this is the case. So if you are to plot this, just like we did with x dot, and fx, now you plot q dot q and f of q. And you get this linear plot, right? So where does it cross this line? It has to be equals to 0, right? What is that line? What is that point? If you solve this, you get q equals c times v0, right? So you basically have one single fixed point, a stable fixed point for this system. Wherever you start, you will end up at q equals c times v0. Isn't this amazing? You don't need to solve anything. You just think in pictures. Do you have any question?
This equation is the conservation of energy equation, so it's pretty easy to derive. Just conservation of energy per charge.
Yes, exactly. Exactly. So you can derive this equation very easily. Let's actually talk about population growth, okay? Briefly. This is another example of 1D system. So if you use this Malthus formalism, do you know Malthus? Yes or no? He said that people the population will increase exponentially, and as a result, you will have misery and vice. Okay, in humans. Well, he is, for most of the part, is right. Anyway, if you use his model, it means that
Somebody has an objection.
yes.
It's not correct.
Yes, it's not correct.
You said it's correct.
Don't we have misery and vice because of overpopulation? Okay. It's much more complicated than that, right? Well, it affected, I believe, Hitler's thoughts too.
Also, best-selling shitty novel, Inferno, was about that also.
Okay.
Yes. The argument was the food production will be linear.
Exactly.
But the growth will be exponential.
Exactly.
Which wasn't true. Our food production is also exponential because of the technologies like fertilizer.
Exactly. Exactly.
Scarce resources. It's like at the end of the day, they'll keep growing, but the food will not keep growing.
Also, the growth rate is not exponential. It's something like this.
Exactly. It's not basically. Let's talk about how were they talking about it? Of course, such exponential growth cannot go on forever. To model the effect of overcrowding and limited resources, population biologists, let's talk about animals, okay? And demographers often assume that the per capita growth rate decreases with n and as n becomes sufficiently large. So basically, the growth actually is crossing some point k, okay, where you have just the right amount of animals, right? Sorry. So, what is the best way of, what is the simplest way of modeling it? It's to assume that this is a line, right? So you end up with this model that is called logistic equation. Do you see? Do you know why it is called logistic equation?
Relation resources, logistics.
Is it because of that? Maybe. So you can see that in this problem, you actually, is it a linear 1D system or non-linear 1D system? Non-linear. Is it non-linear? Yes, it is non-linear because this is growth rate. It is actually, okay, let's write it down here. It is actually n dot divided by n. Okay, so it's different from our plots that we did before. If you do it properly, it will be something like this. Something like this, I believe, right? If we just plot n dot versus n. So you can see that you have this stable fixed point. And wherever you start, you will end up with this carrying capacity of population. Does it make sense to everyone? It's just an example. Don't take it too personal. Okay.
The way of feedback curve in the logistic equation, is it always the case? This is negative 2 or non-negative 2?
What do you mean?
N dot equals RM isn't enough for the logistic equation.
No, you need to have this 1 minus n over k because of what I just mentioned. Like, if you reach that carrying capacity, then animals die because of overcrowding, limited resources, for those kind of reasons. We will come back to logistic equation, and it will be yet another 10,000 citation paper. We will come to that. Okay, are you with me? Yes, everybody? So now we will go to n equals 2. Now we will go to n equals 2, and we will start with linear systems. So basically, for n equals 2, you can simply write it as this one, right? So you have x dot equals to ax plus by, or y, and y dot equals to cx plus dy. Well, you may immediately say that, no, that's not the case. What if I have some e here and some f here, right? Well, you can always transform that kind of problems into this kind of problems. Do you want me to give an example? A nuclear one. So let's say, okay, I will just write at the side of this book. Let's say you are producing palladium in your reactor. Okay? It's an element, and it's radioactive. Okay? And let's say it decays into uranium. Okay? If you are scared, then I will just replace this with x1 and this one with x2. Okay? Let's say you are producing x1 with constant rate, like dx1 over dt is actually equal to s. Okay? But remember, it decays, right? And in the radioactive decay, you have things like lambda 1 times x1. Do you remember this from somewhere? Yes? Everybody have seen something like this? Yes. Then, as it decays into x2, right? So the production of x2 is equal to the rate at which x1 is decaying, plus sign, right? But x2 itself is also decaying. So you have lambda 2 x2. What I'm claiming here is that you can still go to this kind of picture. A, B, C, D, x dot, x1, x2. What you need to do is to define x prime, x1 prime. Let's define x1 prime in the following way. Let's say lambda 1 x1 prime is actually equal to s minus lambda 1 x1. Okay? Then x1 prime, x1 dot, prime dot, sorry, is equal to x1 dot, right? So this equation becomes dx1 prime over dt minus lambda equals to minus lambda 1 x1 prime. So you got rid of s, the constant, right? But then if you plug it in here, if you plug this definition in here, then you will get s back again, right? So what you do is okay, let's plug it in here and see what happens. You will get S minus lambda 1 x1 prime minus lambda 2 x2, right? So you can see the pattern here. You again have this one, and you can define this as minus lambda 2 x2 prime, right? If you do that, then this one becomes lambda 2 x2 prime, and doesn't. So basically, you have this equation x1 prime x2 prime equals to. Are you familiar with this matrix notation? Is it okay? Are you comfortable with it? So tell me, what is our final equation?
The second term in the last equation is in the plus. S plus lambda 1 x1.
This one is plus, right? No, minus. Okay.
Everything is over. Maybe the previous term, lambda 1 x1 prime.
Is this plus?
I guess so.
Yes, it is plus. Thank you. I guess so too. So at the end of the day, what is the first equation? It depends. It's minus lambda 1 and 0 over here. Do you see that? Yes, everyone sees that? And this one has lambda 1 and this one has minus lambda 2 over here. So you can see that we can always get rid of these constants. Am I convincing enough? Yes. So you will always end up with this kind of equations after all. Now, how do you solve these kind of equations? No idea, right? So you basically, to find the condition on, okay, I skipped some parts, but basically you propose that you can have a solution in this form, which means that as you can see, it's bold, so it means it's a vector. So basically we are talking about a solution, a possible solution that is in the form of e to the lambda t v1 v2. Now remember, we started actually the art of computing by defining exponential and how it is important, right? Remember, we said that it's a very important function because its derivative is related to itself, right? So if you let's do this over here, somewhere over here. So we had some equation, right? X vector, dx vector over dt. By this one, I mean this one, dx1 over dt, dx2 over dt. Are you still with me? Is the add drop time passed? So we basically say that this is equal to a times x, right? So just like in the case of, let's give an example, like dx over dt equals to ax. Just like there, you can, what we did there, we proposed the solution e to the alpha x, and it would give you alpha times e to the alpha x equals to alpha a e to the, no, this one is without alpha, e to the alpha x. Do you remember this? So a was alpha, then your solution would be like e to the ax, right? Now we are doing it for matrices. I feel like I'm confusing you completely. Am I? Yes, you are right. Thank you for that, for being here to save me. Okay, perfect. That actually was confusing myself too. So basically, let's follow this equation. So we had dx dt equals to ax. And we propose that x is equal to e to the alpha t times v. Any problem so far? No problem. Then we put it into this equation. What's the derivative of x? Dx over dt. Look at here. What's the derivative with respect to t? Come on, speak, people.
It's alpha e to the alpha t v.
Okay, alpha e to the alpha t. Do I need to point at you for you to speak? you are perfectly right, right? Then I can simply write it down as alpha e to the alpha t v vector, which is this part, equals to a times, remember x was e to the alpha t v vector. So you can see that this goes away and you end up with this beautiful equation. Alpha v equals to, let's instead of alpha write lambda. Do you know what these equations are called? Eigenvalue equation, right? I think it comes from German.
Yes.
What does it mean?
I don't know. It's hard.
It has to do with the self. Okay. So how do you solve these kind of problems? How do you solve eigenvalue equations? Basically what you do is you need to solve this equation, determinant a minus lambda identity equals to 0. Okay? So basically you need to subtract lambda from the diagonals, right? And then find the determinant which can be expressed in this form, where tau is the trace and this one is the determinant. And then lambda 1 is this one, lambda 2 is this one. Okay? We are going somewhere, and when we do examples, you will see that it really works. Is it the end of? Okay, it's the end of the book. So I will do something else. Let's actually look at one particular example of the system, and I promise you will understand it, but you need to be really with me, okay? You need to be really following all the calculations, and whenever it's unclear, just let me know, okay? So let's say I have this system that has x1 dot equals to x1 plus x2, okay? And x2 dot equals to 4x1 minus 2x2, okay? In our representation, it's basically x1, x2 dots equals to 1, 1, 4 minus 2, x1, x2, right? Now let's find the determinant of this one. So 1 minus lambda, 1, 4 minus 2 minus lambda. So you multiply these two and you subtract from the multiplication of these two, right? What do you get? Minus 2 plus lambda, right? Plus 2 lambda plus lambda squared minus 4 equals 0. Am I correct? Lambda squared. This one is minus lambda. Thank you. Okay, I know the result, so this is the result. Okay, and if you actually do the calculation and then you find lambda 1 equals to 2 and lambda 2 equals to minus 3. Okay. Then I didn't mention eigenvectors. Okay, I didn't mention them. Those are the things that go with these lambdas. Do you remember e to the alpha t, or let's just write e to the lambda t? There was some v here. Okay. Yes. So for each of these lambda, we will find some kind of v. Are you still with me? How do you find? You plug it back in this equation, 1 minus lambda, in this case 2, right? Then you have 1, then you have 4, then you have minus 2 minus lambda, which is 2, okay? And the multiplication of this one with this vector has to be 0, okay? All this, it has to do with linear algebra, and you can find it in any book you want, okay? I have to skip these parts really quickly, so I'm sorry about that. But what you notice is that these equations, you have two equations here, right? And they are both can be solved with one solution, which is V1 equals to V2. If V1 equals to V2, then it's minus V1 plus V2 is 0, and 4V1 minus 4V2 is 0. So basically, your eigenvector is V equals to 1, 1. So what happens is that the first eigenvalue was lambda 1 equals 2, and the corresponding eigenvector is 1, 1. It could be AA. You are right. It could be AA. That's perfectly correct. But the important thing is the ratio. We will actually do something related to that point in a moment. The other one, I will tell you what the result is by cheating from the book. What was lambda 2? Minus 3. And if you do the calculation, it turns out that the corresponding eigenvector is this one. Okay. The nice thing about the linear systems is that you can express now the solution, by which I mean the general solution for x1 and x2 can be expressed as some constant c1 times e to the minus lambda 1 minus or plus lambda 1 t v1 vector plus c2 e to the lambda 2 t v2. So if we plug in the results, so our general solution is the following: e to the 2t plus c2 e to the minus 3t 1 minus 4. Let's move one more step, and then the general solution is that you should have something like this and something like this. Are you still with me? Still, this is more familiar to us, but let's keep this way. Let's keep it this way. And what you are seeing here is that you have two vectors. Okay. Let's draw x1, x2. Let's remember that our problem was something like this. So if both of the points here is 0, what do I get as x1 dot and x2 dot? They are also 0, right? Which means that the origin is always a fixed point, a point where it's similar to those fixed points that we had, the unstable, stable one, etc. Right? Now let's draw the arrows here. Let's draw the vectors here. Sorry, 1, 1 is a vector that goes like this, right? And on top of that vector, you can see that you have e to the 2t, which means that if you start from here, you will explode to infinity, like this. Or if you start from here, you will explode to infinity. And then there is another vector, 1 minus 4. Okay? Basically, you can write down this vector by writing x1 minus 4x2 equals 0. Okay? Just trust me with this. And that vector has something like this. And what is the eigenvalue? What is the function? It's e to the minus 3t, right? And what is it doing? It should approach this point. You can see that now we have a different kind of point. It's neither unstable nor stable, right? At some direction it's actually attracting, at some direction it's actually repelling. So when we solve this, we will see that the trajectories will be something like this. Do you see my point? And over here it's something like this. Do you agree? Oh, okay. Sorry. So this kind of points we call saddle point. Do you know what saddle is? Something like this. You put on the horses, right? Why the saddle point? Because, for example, saddles have in this direction, they are, if you place a ball over here, it will fall down here, right? But if you place a ball over here, it will fall down here. So in one direction it's attractive, in the other one it's repulsive. Okay? How much time do I have? 20 minutes, right? We have plenty of time. So if you missed this point of lambdas, eigenvalues, eigenvectors, and everything, we can talk one-on-one. You can go to some linear algebra book, doesn't matter. But that's not really the point, okay, of this course. And for sure, the point is not to scare you off. So, actually, I'm surprised that my presentation finished there. I have to have more slides. Let me check one thing. Yes, I have one more slide to analyze. And this is like one of, and again, those points where the book is just being divine. Okay. So remember, you always derive some lambdas, right? Do you remember that? We had A equals A, B, C, D, and we basically solved this equation, A minus lambda times D minus lambda minus CB equals 0, okay? And from here, we found lambda 1 and lambda 2. So this plot actually shows you what you will have. I mean, how your point x1 equals 0 and x2 equals 0 will behave. This tells you that. So you can see there is this delta, and whenever delta is negative, you have a saddle point. Did we just have a saddle point? Just in the example. Let's check whether it agrees with the plot, okay? So how do you calculate delta? By multiplying lambda 1 and lambda 2. So delta equals to, what was lambda 1? 2. The other one minus 3, and you get minus 6. So you have a saddle point, okay? And these ones are unstable nodes, so basically they will repel in all and every direction, right? These ones are stable nodes that are attractive in all directions. Then if you are around here or around here, you actually have complex lambdas. Okay? Complex lambdas means that you have something like a plus ib, right? So e to the a, we know what it does. It's either explodes or decays, depending on a is positive or negative. What about e to the ib? Do you remember what it was? Cos b plus I sine b. So in 2D, you will have oscillations. In fact, you will have stable spirals, which mean that if you are in this region, wow, this looks really nice on black. Then you will have something like this, spirals that go down to a point. If you are around here, then you will have an unstable point that would spiral out. Okay? If you are exactly here, then you will have periodic orbits. I mean, what is the thing between an unstable and stable spiral? A circle, right? Are you happy to see all this? Of course, if we have time, let's actually code the thing that we just did. Okay, since we don't have too much time, I will just open something for you. So here I'm dealing with this equation that I have just shown you. X1 dot equals x1 plus x2, and x2 dot equals to 4x1 minus 2x2. So here what I'm going to plot is the derivative, the direction that the system takes at each point. And I also draw our lines. Okay, let's make it big. You can see that, okay, by the way, apparently I did a mistake. The 1 minus 4 line looks like this, not like this. Okay, are you with me? So you can see that this is a saddle point indeed. It attracts in one direction, and okay, which direction is that? This direction is attractive. Do you see the arrows on top? They are always going towards this center. What about these lines? They are always leaving out, right? So you start from here, you will go here. You start from here, you will go here. You start from here, etc. Right? Let's look at an example. Am I that boring? Okay, I still have some time. So let's, for example, look at a simple harmonic oscillator. What was the equation for it? M times the acceleration is equal to minus kx, right? So you can write it down as d squared x over dt squared equals to minus k over m x. Okay. May I call this omega squared? Yes? Then I will also call v, the velocity, is equal to dx over dt. Then I can say that dv over dt is equal to minus k over mx. So basically I can write it down in terms of x1, x2 dot, the two dots here, equals to what? Yes, I will point at you so that you can speak. Speak.
X1 dot is
It works.
x minus omega squared.
I think that's x2 dot. So if we assume that this is x1 and this is x2.
So it's 1, 0.
Very good. The first one is dx1 over dt is equal to actually x2, right? Dx1 over dt equals to x2. What it means? 0, 1, right? The other one is dx2 over dt equals to minus k over m times, or omega squared x1, minus omega squared x1. Then what do you have? Minus omega squared here and 0 over here. Do you agree?
What are the two set of equations that you realize?
Two set of equations. It's this one and this one. Okay. So let's find the eigen values. Okay, eigenvalues. Minus lambda. It's very easy for this system. So lambda squared plus omega squared equals to 0, right? So lambda is plus minus I omega, pure imaginary eigenvectors. Let's see what should we get in that case. So what is lambda 1 times lambda 2? Minus omega squared. And
so omega is complex.
no, it's plus omega squared. It's minus I omega times I omega, which means minus. So we are not a saddle point, right? What about lambda 1 plus lambda 2? 0. So we are on top of this one, which is a center. Yeah, I mean, centers mean that around those points you will always revolve, right? So basically, if we are talking about x1 and x2, this is what you get. If you start from here, you will revolve around here. If you start from here, you will revolve around here. Which is what you expect from a harmonic oscillator, right? We have 7 more minutes of torture. And I will use every bit of it. So what about damped oscillator? How hard it was to solve that problem, right? Now d squared x over dt squared plus kx. We had these terms, right? Now let's add plus b times dx over dt equals 0. If we are talking about physics, this means that ma equals to minus kx. This was the spring force. But you also have now b times v, which is dissipation, a bit friction, right? Or drag. Better? Damper, exactly. You are damping the oscillation. Where does this b go in this equation? You can see that you have an extra term. Before we had minus w squared times x1. Now we have also minus b times x2. Do you agree? Yeah, b over m. Minus b over m. So there is something here. Let's solve this. What should we get? So you have minus lambda 1 minus omega squared minus lambda minus b over m. Can I call it b? Just b? I can always do this. Actually, when you are doing that, then you should use gamma. People do that, so let's use gamma. Okay, what's the result of this calculation? You have to help me out. Gamma, yes, gamma. Over here. So just trust me that lambda will have, I guess, something related to gamma, actually minus gamma probably, plus minus I omega. Something related to it, I guess. So my point is that, let's go back to this system. It will be one of those stable spirals. If you do the calculation, just trust me, it will be a stable spiral. And I just want to show you that it indeed spirals in. Not spirals out, but spirals in. I think this was it, yes. So you remember we introduced this ODE 45 before? So now I have, I start from 1 and 0. And let's look at the equations. Dx1 over dt is x2. Do you see it? And dx2 over dt is minus w squared x1 minus b times x2. Are you with me? Yes? What happens if I if I say b is 0? I should get a circular orbit, right? Let's run it. And I get a circular orbit. Do you see it? Yes? X and V are in this case symmetric, but if I change omega to 2, then you will get an ellipse. Because they are two different things. This is position, this is velocity, right? What do you expect to get? Let me put it 1 and let's get 0.3. What do you expect to get? Spiral in, right? Do you see? It's beautiful. Yeah. And what do you expect if you have an damper or whatever. Like, this is unphysical, but still, what do you expect? Yes, spiral out, right? Well, you don't see where it starts really, but you can see from this that it's 10 to the power of 6. Do you see it? So it really spirals out. We start from here, it spirals out. Actually, in fact, uh, I had a code that had animation in it. Maybe this one. Let's try this one. Hope it works. Spiraling in, right? And let's try minus. Okay. Let's make it. Let's change the axis to minus 10, 10, 20, 20. Spirals out and really quickly. Okay. Any questions?
Historical point. These systems are called linear systems, and the solution for such systems were found at the beginning of 19th century by Lagrange. And
Okay.
until that moment, everybody was so good at Newton mechanics. They were able to solve so many one-particle problems, but they were thinking over that time to be able to solve an n-particle or complicated system.
Yes.
Was so difficult, so we cannot handle this. And nobody was expecting to find eigen solutions for such systems, which
Yes.
we have found already, which makes the system so easy to understand internal modes and how we can affect those constituent parts. So it's a revolution.
Exactly. By Lagrange, you say. Exactly. So I feel bad because it's indeed a great revolution, and I feel like I didn't go through it in detail. But please, maybe with homeworks, with extra things, we will catch up with these linear systems because we need to understand them very well. Because in next lecture we will start dealing with nonlinear systems, and you will see that we will deal with them by linearizing them, actually. So this should be perfectly written in your brain so that you can use it whenever you want. Thank you all for coming. See you next week.